Welcome to video lecture F7. This one is a factorization lecture on the QR factorization of matrices. I'll be your demonstrator, Tom Roby, and here are the outline and objectives. We'd like to apply the Gram-Schmidt orthogonalization process that we just learned to construct something called the QR factorization of any m by n matrix A whose columns are linearly independent. So if the n columns are linearly independent, that means that the rank of A is n, and that means in particular that n has to be less than or equal to m here. So in that case, we can factor A as a matrix QR, where Q has the same dimensions. It'll also be an m by n matrix. And then R will be an invertible n by n matrix, which will be upper triangular and have a certain other property. So let's see how this works. So suppose that, here's the theorem. Suppose I've got an m by n matrix. It has n linearly independent columns, so rank n. Then when I factor it, I get this matrix Q is an Rm by n, and its columns are an orthonormal basis for the column space of A. So the way I'm going to get Q is just exactly by using Gram-Schmidt orthogonalization. I'll just take the columns of A and Gram-Schmidt them so that I get the columns of Q. Now R will have these other properties. It'll be an upper triangular matrix and it'll have positive diagonal entries. So let's see immediately on an example how this works. So here I've got a 4 by 3 matrix, right? So M has to be bigger because these three columns have to be linearly independent, which means that we have to be in at least R3. Here we're in R4. And the usual Gram-Schmidt algorithm, I'm not sure it's worth showing it to you again right now, but you might want to check at home and double check my arithmetic, make sure this is correct, that if you Gram-Schmidt these guys, these three vectors, then you get these three vectors. How do you see that? Well, I mean, the first column should be the same, right? And then the second column I should get by taking, by projecting this vector onto that vector and subtracting it from this vector. So I should have minus 1, 2, 3, 4, and I should be subtracting from it some multiple of 1, 1, 1, 1. In fact, that multiple of 1, 1, 1 turns out to be 2, and so that's why I get negative 3, 0, 1, 2. And similarly, you project this onto the subspace span by the other two, and so you get this nice orthogonal set of three orthogonal vectors. Now remember that a matrix is not orthogonal if it has orthogonal columns. It needs to be square and have orthonormal columns. And here we don't even have a square matrix. But we do have, it's now orthogonal, and you can just check at least that that's true, right? That's easy to do because here we'll have minus 3 plus 0 plus 1 plus 2, so that dots to 0. Here we get 1 minus 2, so I've got minus 1. Another minus 1 is minus 1, minus 2 is minus 1, then another minus 1 is minus 2, plus 2 is 0, good. And now here I'll have minus 3, 0, still minus 3, so then minus 3 minus 1 is minus 4, plus 2 times 2 is 4, good. So there's some good chance that I did that right, because at least in the end I got a basis that was orthogonal. And now I just normalize each of these vectors by dividing by its norm. So the norm of this is the square root of 4, which is 2, so I'm dividing by 2 everywhere, so this vector is all a half. Here I'll be dividing by the square root of 14, and this last one I'm dividing by the square root of 10. So that's my matrix Q. It's still the same dimensions. It's a 4 by 3 matrix, but now is this nice property that the basis, that each of the columns, the set of columns is orthonormal. And one of the things we know when we have a rectangular matrix whose columns are orthonormal is that Q transpose times Q is the 3 by 3 identity matrix. Okay? So, I mean, I found Q. How do I find R? And here's the key thing, is that R comes out of this incredibly simple but neat algebraic trick. So if Q transpose Q is equal to the 3 by 3 identity matrix, if I want to find A equals Q times R, and I found Q and I know A, how can I get R? I can't divide by another matrix generally, but here basically Q transpose has given me a one-sided matrix inverse. And so I can just multiply both sides of A equals QR of this equation. I just multiply that on each side by Q transpose. can't stop me from doing that, right? So Q transpose times A is equal to Q transpose times Q times R. Associative property still works, so this is Q transpose times R, and we just say Q transpose times Q is the identity, so we just end up getting R. So in other words, the point is that we've computed R now is just Q transpose times A. So we just take the original we take the Gram-Schmidted matrix, take its transpose, multiply it on the left of A, so that's what we get here. That'll give us R. So here I've taken this matrix, I've taken the transpose, as you can see, and now if you do this matrix computation, you'll find, lo and behold, that you got zeros below the diagonal as advertised, and along the diagonal we get these vectors that I've marked in green, and you'll notice that they're all positive. Okay? So that's how to do the QR factorization in practice. So once the hard work is all in the Gram-Schmidt, and then the rest of it is just making sure you don't make an arithmetic mistake, because if you're doing it by hand, you probably have square roots in the denominator. But notice that the square roots don't really bother you in the sense that it's the same square root everywhere, right? So for example, if I wanted to check that, say, that middle entry is 14 over the square root of 14, which I could have simplified to the square root of 14, but there was no real advantage here to doing that, then what do? So here I have, 3 over the square root of 14 plus 0 plus 3 over the square root of 14, so that's 6 over the square root of 14, plus 8 over the square root of 14. So it's really 14 over the square root of 14. I'm really just doing integer arithmetic and carrying my denominators along for the ride. Okay. So that's the QR factorization, but why does it always work? And why in particular did we get those, the zeros on below the diagonal and the positive vectors on the diagonal? And the key thing there is this property that we made note of when we were looking at Gram-Schmidt, which is that at each stage of the process, it was always true that the span of the first k vectors, so now I'm calling u1 through uk are the vectors that I'm creating via Gram-Schmidt, and I want to think about my matrix Q then is going to be the matrix u1, u2, uk. I guess I've got n columns, so it's u1 through un. Okay? So what does that mean in practice? Well, that means in particular that I can write x sub k in terms of u1 through uk. I don't need the rest of them. I only need to go to the kth one to write xk. So that means I can write as a linear combination, so I just do that. I write it as r1k u1 plus dot 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 plus rkk uk. So each of these scalars that I'm writing is just r something k times the corresponding u sub I. Okay. Now in terms of the whole basis, since I really have n of these things at the end of the day, that means I really have plus 0 times uk plus 1 plus dot 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 plus 0 times u sub n. Okay. But what that means, and I should say that, r sub kk has to be bigger than or equal to 0, or I could just change the sign of u sub k to make this work. So, I'll always do that, if I need to change the sign on some u sub I in order to make sure that I have positive things on the diagonal, then that's what I'll do. All right, so now let's just set r sub k to be this is really a column vector, r sub 1k, it's the coefficients on this linear combination. Okay? And what this expression is really saying then is that if I take q, which is this set of vectors, and I take the linear combination of that given by this vector r sub k, that I get x sub k. Okay? So that's what this equation says, right? It's just a translation of this equation into shorthand. Okay, but now we're basically done, because now all I have to do is to let R be the matrix of all these R's, and so I got that each of these x sub k's was equal to q times r sub k, so that means that if I put them all in a matrix, column by column, that column by column, x1 is qr1, dot dot dot, xn is qrn, So that's just equal to q times r. Okay? So there it is. It's just an easy thing to see. And I guess you might ask a few questions, like, first of all, why is R upper triangular? Well, that's this property, right? This property that says that when I write down R, so maybe I'll write a little bit here. When I write down R, so to write down x1, I'll only need R1 1 times U1, and all the other ones will be 0. So that means if I'm thinking about writing x1 in terms of this basis, that I'll only have R1 1 here, and then everything else will be zeros. Okay? Now for the next one, I'll need an R1 2 and an R2 2, but all the rest will be zeros. And then I just keep going like that. For the last one, R1n, I'll actually need R2n. I might need to go all the way. But all of these guys will be zeros. Okay? So that's why it's upper triangular. It's just the construction. Why is it invertible? So I said I could assume that R sub kk was bigger than or equal to 0, and maybe I could make an argument just in the middle of this to show that R sub kk had to be greater than 0 because, well, I know that these guys are linearly independent, right? So that, you know, I'm going up a dimension every time I add an x sub k, which means I need to go up a dimension every time I add a u sub k, which means that coefficient has to be non-zero. But there's another way to argue it, which is just from the way QR works. And this is kind of nice because it's helpful to think about things this way. So why is it invertible? Well, if I think about, so I'm trying to think about A as being equal to Q times R, right? So what does that mean? And A is we decided what its dimensions are, right? A is an m by n matrix, which means that it represents a linear transformation that's going from Rn to Rm. Now Q is also going from Rn to Rm, and then R is just going from Rn to Rn. So what does that mean in terms of my blobs? So that means that Q is going from R to the n to R to the m, and then right? Not quite right, because when I do A equals QR, I do R first. Okay, so what that means is that I need to do R is going to go, this matrix R is going to go from R to the n to R to the m, and then it's followed by Q, which goes from R to the n to R to the m. So A, on the other hand, is the combination of these things, right? So this is the same as the transformation A, which goes from R to the n to R to the m. Okay, so now, how do I show that? How do I show that R is invertible? Well, if R wasn't invertible, then what would happen? If R wasn't invertible, then since this is a square matrix by the invertible matrix theorem, it would have to have a null space that wasn't just 0, right? So the things going to 0 would include, so the null space of R would have to be bigger than 0. It would have to have some dimension. Okay? But if that's true, then the null space of A would have to have some dimension. But we know that A has linearly independent columns, so it doesn't have any null space. When you row reduce it, you're going to get n pivots, and you won't have any free variables. Okay? So if R were, right, and so, but if the null space of R is bigger than 0, if A is equal to Q times R, well, then anything that went to 0 here will definitely go to 0 there. So if I have a non-trivial null space, for R, then I must have a non-trivial null space for A, but I don't have a non-trivial null space for A, so it can't happen. All right, so that's one way of seeing that R is invertible. And once you know R is invertible, then since it's triangular, so the next question is, why are all the diagonal entries positive and not just non-negative? Well, if one of the entries was actually 0, then this determinant would just be 0, right? But we know that an invertible matrix has non-zero determinant, so this can't be. So none of those entries can be 0. Okay, so those are the answers to those questions. And I think that's it for QR factorization. It's just a nice way of thinking about Gram-Schmidt, but it does have applications where you use the QR decomposition of a matrix to do certain kinds of computations involving, for example, least squares, which we're going to get to soon. So that's it. Thank you for your kind attention.